All right, so we're going to talk about quantum numbers now. So quantum numbers describe the probability distribution, describe the orbitals that I mentioned on the last slide. So now we're going to talk about those quantum numbers that are defining our orbitals. So the first one we have actually seen before is n. N is the principal quantum number. We saw it when we were talking about the Bohr model for the hydrogen atom. N describes the size and energy of the electron shell. So that means the size and energy of the orbital. So this is that representation of a electron density map for an atom. So we talked about N when we talked about the Bohr model and how N, when N is higher, the electron has more energy and it's further away from the nucleus. And that's all that we're seeing here. So this inner circle is n equals 1. This outer circle is n equals 2. And this furthest biggest circle is n equals 3. So it's getting bigger the higher the value of n. So n is still an integer like it was in the Bohr model, 1, 2, 3, 4. It can't be 0, so it starts at 1 and goes to infinity, but it's a whole number. And it's describing the probability of finding the electron in these orbitals. So the probability of finding the electron this far away from the nucleus, so that's where it drops to 0, basically. The probability of finding that electron drops to 0 at the boundary of the n equals 1 orbital. If you give the electron some more energy, and it can go up to a higher energy level, that means it can get further away from the nucleus, and our probability distribution of finding the electron expands. So that's what n tells us, the size and the energy of the electron shell. All right, so now let's talk about a new quantum number. So the angular momentum quantum number is L. So I made it like a cursive L. That L describes the shape of the orbital. So L is going to be an integer as well, but it can't be the same as n. So it has to be 1 less than n. So here, if n equals 1, L has to be 0. If n equals 2, L can still be 0 or 1, but it can't be any bigger. If n equals 3, again, L can be 0, it can be 1, or it can be 2 now, but it can't be 3. It can't be the same as n. It has to be less than n. And this angular momentum quantum number L describes the shape of the orbital. So sometimes we'll have these spherical orbitals like we saw on the previous slide with our probability distribution, but sometimes the probability distribution gets a little weird. There are certain areas where you'll never ever find the electron, like this node right here in the middle, and all this space over here and over here. You're only going to find the electron in these lobes for this number of L. And L is just going to tell us where it's most likely to find the electron, and it's most likely to find the electron in these lobes. So depending on the value of L, that will tell you the shape of the orbital, whether it's spherical or some other type of shape like this, where there's like random spots like these corners of the clover, where you'll never find the electron, even though you could find it in a spherical orbital. You won't find it in this version of the orbital controlled by L. And finally, there's the magnetic quantum number, m sub L. So when something is subscript, so we have m and then a little l, subscript, so I'm going to call that M sub L from now on. So M sub L describes the orbital's orientation. So now these are all these dumbbell shaped or figure eight shaped orbitals, and M sub L describes the orientation, whether it's along the x-axis, the y-axis, or the z-axis. For example, with this certain value of L. So we learned that L has to be less than N. There's also rules for the magnetic quantum number. M sub L can be anywhere between positive L and negative L. So if L is 1, M sub L can be -1, 0, or 1. So it has to be between negative L and positive L, and it's still an integer. So the only three options are -1, +1, and 0. 0 is an integer that you can use in the case of L and M sub L. Okay? So here's a table that goes over all of that. When N is 1, L can only be 0. It can't be 1. And when L is 0, M sub L can only be 0 because there's no such thing as plus or minus 0, just 0. When N is 2, we have more options. So, like I said, L can still be 0, or it can be 1, but it can't be 2 because 2 would be equal to N. So L can be 0 or 1. When L is 0, M sub L can still only be 0. When L is 1, I showed you this one, M sub L can be -1, 0, +1. The more we go up with N, the more options we get. So N equals 3, L can be 0, 1, or 2. And when L is 0, we still got the same option. When 1, we got 3 more options. And then when L equals 2, we can go to -2 and +2. So we add in 2 more options for M sub L. So the bigger N gets, the more options for M sub L over here, and the more options for L as well. Okay? This table is going to be really, really helpful for you guys to learn these rules. All right, so I said that L defines the shape of the orbital, or the shape of the probability of finding the electron. So what does that mean? How do we know what shape it is based on what L is? Well, when L equals 0, the orbital is an s orbital, a sphere, like the first orbital we saw, that example. When L equals 1, it's a p orbital. A p orbital is this figure 8 or dumbbell shape. When L equals 2, it's a d orbital, which typically looks like a clover. There's one option that doesn't look like a clover, and it looks like this. It's a figure 8 with a little donut around the middle, and that is the dz squared orbital. Just so you know that it exists. These are all D's. And then F orbitals are when L equals 3, and an F orbital is a really weird shape, so we don't draw those. So you guys don't need to know what that shape looks like. So always when L equals 0, it's going to be an s orbital. Always when L equals 1, it's going to be a p orbital. Always when L equals 2, it's going to be a d orbital. Always when L equals 3, it's going to be an f orbital, okay? So you should remember those together. 0s, 1p, 2d, 3f for L. All right, so now we can describe our orbitals using our quantum numbers. If n equals 1, L has to be 0 because L can't be equal to n. And then if L is 0, m sub L has to be 0 because there's no such thing as plus or minus 0. And that means that it's an s orbital, and we call it the 1s orbital because we put the n at the beginning. So the number tells you about n, and the letter tells you about L. Okay? So when n equals 2, we have two options. So we have the same option that we just talked about with the s orbital, and that one's called the 2s orbital because now n equals 2. But we also have the option of L being equal to 1. So if L is equal to 1, it can be 1 because that's not equal to n. It's still less than n. So if L equals 1, then again, m sub L can be -1, 0, or +1. And these are the three 2p orbitals. So the 2 comes from the number, or sorry, the 2 comes from the n, and the p comes from the L equals 1 if we look back up here to our table or definitions. Okay, so when you're given a number and a letter, that tells you the n and the L quantum number. All right, let's keep going. So what about when n equals 3? Which of the following is a possible combination of quantum numbers? Let's write out our possible quantum numbers like we had in that table. Okay, so n equals 3. So what can L be? L can be 0. L can always be 0. L can be 1. That's still less than n equals 3. L can be 2. That's still less than n equals 3. But L cannot be 3 because n cannot equal L. L has to be less than n. Okay, so those are our three values of L. So that eliminates this option right away. So our other three are still competitors. So let's look at m sub L. So m sub L has to be 0 when L is 0. What about when L is 1? When L is 1, we've got -1, 0, +1, like I showed you before. What about when L equals 2? So we can go to plus or -2. So -2, -1, 0, 1, 2. Those are all of our options for m sub L based on our L value. So let's look at our choices now. So L equals 0, that's fine. But when L equals 0, m sub L has to equal 0. It can't be -1. So that's it. And let's look at the next one. So L equals 1 and m sub L equals -4. So that's also not good because L has to be, so if if L is equal to 1, then m sub L has to be between negative and +1. It can't be -4. It can only be these three options. Okay, so that narrows it down. So can we do this one? Let's just double check and make sure I didn't make a mistake. So if L is 2, m sub L can be any of these numbers, so it can be 0. Yeah, awesome. So that's how you decide which of the following is a possible combination of quantum numbers. What's next? So there is actually a fourth quantum number. I know I only said there were 3 before, but there is a fourth, and that one is called the spin quantum number. So the only thing that this one tells us about is the spin of the electron. It doesn't tell us about where it is based on size or shape or orientation. It tells us about the spin, not the location. All right, so scientists found that you can split lines in an atomic emission spectrum using a magnetic field. So remember those emission spectra that we had, like for hydrogen, there was a purple, there were like 2 blues, and then there was a red. Scientists found that if you use a magnetic field, if you put a magnetic field near your gas discharge tube, that you can split one of those lines, or all of those lines really, into 2 separate lines. And that told us that there must be something magnetic about electrons. We can't see the spinning of electrons, but we know it exists because the electrons themselves have these magnetic fields. So why would an electron have a magnetic field? Because it's a spinning charged particle. Based on the rules or the laws of electromagnetism, if we have a spinning charged particle, it produces a magnetic field. So because we know that there are magnetic fields, because we can show them using our atomic emission spectrum, then we go backwards and can say that the electrons must be spinning for them to be making magnetic fields. Okay, so this is what the spin of the electrons look like and how it makes a magnetic field. So when it's spinning counterclockwise, our magnetic field points up towards north. And if it's spinning clockwise, our magnetic field points down towards north. So this is just like the Earth. The Earth is spinning in space. That's why we have days. That's why we have day and night. So the Earth is spinning and it has a magnetic field. And you might have heard, it's a fun fact, that dogs like to line up with magnetic field lines when they go to the bathroom. So that's a fun fact. We don't know why, but they do. Anyway, back to electrons. Electrons can only be found in 2 spin states. So there's only clockwise or counterclockwise, which means there's only up or down magnetic fields. So we call the spin quantum number m sub s, and it can only be -1/2 or +1/2. And I think the 1/2 is a pretty arbitrary number that they came up with, but it adds up to 0, so that they cancel each other out. That's the important thing, is that they're the same thing. And you can only describe half of the electrons using one of the spins and the other half using the other spin. So maybe that's why they called it 1/2. Not too sure, but that's not important. What is important is that it can only be -1/2 or +1/2. So we had all those other rules for n, l, and m sub l, but the only rule for m sub s is that it's positive or negative 1/2. That's the only rule. And these spin states are represented as up or down arrows in orbital diagrams. So this is something called an orbital diagram, which we'll see a lot more in chapter 4. And the electrons are represented as arrows, and the spin state is the direction of the arrow. So this is an electron with an up spin, and this is an electron with a down spin. This is an electron by itself with an up spin. Note that when we have both spins together in the same orbital, so we have an up and a down in the 1s orbital, that means we have 2 electrons in the 1s orbital. One has to be up, one has to be down. They can't both be up or down because that would make the orbital unstable. So if there are 2 electrons in the same orbital, one has to be up, one has to be down, and those are called paired electrons because they're in a pair in the orbital. Okay, so here's a nice little experiment that was done to prove that electrons spin. What they did was they heated up a gas in this oven, which caused it to act like our gas discharge tube. It discharged a beam of gaseous atoms, and they shot it through this screen, and it went through this magnet, and this magnet is creating a non-uniform magnetic field. So you can tell because the magnet is kind of differently shaped on the bottom than on the top. So we've got a non-uniform magnetic field. When you do that, that means that half of the electrons that are spinning, well, all of the electrons that are spinning clockwise, which is half of the electrons in the beam, are deflected up, and the other half that is spinning counterclockwise, those are deflected down. Okay, so you can tell that electrons are spinning because they separate in this way, and we can see it on a detector. And the reason that it's about half that spin clockwise and half that spin counterclockwise is because they're random. The spins are random, so some of the electrons are going to be spinning one way and the other electrons are going to be spinning the other way because it's random, so it's about 50-50. Okay, so that's it for quantum numbers, sort of. We're going to talk more about quantum numbers in the next section, but the next section is going to be about orbitals. So let's just get one more practice question on quantum numbers by themselves. So what is a possible set of quantum numbers for a 6p orbital? So this 6 tells us that n equals 6, right? That number tells us that n equals 6. So A is out because n doesn't equal 5, it equals 6. What's this p tell us? P tells us that L equals 1. Every p orbital has the quantum number L equal to 1. This is how it always works. So that gets rid of D. So now we're down to B and C. So let's see. What else can we tell about these choices? So I look at these choices and right away I see that B has an m sub s equal to 0. That's not possible. M sub s has to be minus 1/2 or plus 1/2. The electron has to be spinning. So our answer is C. And we can check to make sure that it's legit. N equals 6. So L can be 1, sure. It's not equal to 6, it's less than 6. M sub L can be equal to 0 because it's between negative and positive 1. And then, yeah, M sub S is positive 1/2. So that one's a good one. You're going to get lots and lots of questions on quantum numbers, and it's all going to be based on these types of rules, okay? So let me pause here, and then we'll go on to orbitals.